Hey everyone, geophysicist Stefan Burns. We right now have supercharged radiation belts. This is a specific energy level around the planet. I consider the Earth being like a energy onion. There's these different shells of energy going from the core to the mantle to the crust to the atmosphere, and then out into space you have the radiation belts, and they can have variable flux. So there can be a high amount of electrons and a high amount of protons. There can also be a very low amount of these extremely high energy relativistic particles, meaning that they are traveling near the speed of light, because Earth's magnetic field acts as a particle accelerator. Well, what we're seeing right now in terms of the flux in the radiation belts is something that we don't see all that often, especially during solar minimum. We are right now in solar maximum. We just had a big push of electrons into the radiation belts from this high-speed stream impact, and we have a coronal mass ejection impact probably coming in the next 24 hours. It looks like we have a pretty surefire hit coming in. I can show you that with our coronagraph here, and this is differential, and you can see this push come out on all sides right there. So it's a weak partial halo coronal mass ejection that launched from the sun towards the Earth. And these sort of solar storm impacts, what they do is they cause the radiation in the belts, these electrons and protons and other relativistic particles, to then rain down and precipitate into those deeper energetic layers. So that would be the ionosphere, the uppermost part of the atmosphere. It's about 1% plasma. Whereas everything in the radiation belts is basically plasma. And then even down into the atmosphere, like the troposphere where we live, and then down into the crust. Because once you enter the ionosphere and hit that region, about 50 kilometers up during daytime, but really strongly at 300 kilometers, going all the way to 1,000 though, above the surface, then you can start to create these really powerful electric currents and alter the electric field potentials, and now you have a strengthening of the global electric circuit. You can increase the atmospheric conductivity profile that can alter local weather systems. We see traveling ionospheric disturbances, sometimes before, during, and after earthquakes, like immediately afterwards. And so it can change a lot of things closer to the surface. So the radiation belts are worth paying attention to. And this is really interesting because it's a perfect example. Look how charged up they got. Let me actually pause the video at the very end there. I mean, we don't see them reach charge levels like this all that often. They are supercharged right now. And it's really clear because we have this high-speed stream impact coming in, and then we see them immediately charge up. So let's actually break down that chart. Hello and welcome everyone. I'm your host Stefan Burns, geophysicist, space weatherman, and more. What we cover on this channel is what's happening energetically on Earth at any given moment by examining all the factors. We look at everything. So geologic events like earthquakes, volcanic eruptions, also geophysical energies, Schumann resonances, how they change. These overlap with us biologically, also mentally, and perhaps even consciously. We also look at solar activity, space weather, planetary resonances. We have some insane planetary resonances right now. Looks like we're going to have a big wave of solar activity coming our way as a result of this geometric alignment. I'll talk about that briefly in this video. And then we also zoom out to cosmic forces. Recently been looking at like nova explosions, their effect on Earth. Really interesting stuff. We've had 2 nova explosions just in the past 2 weeks or so. One on June 12th, another on June 25th. And we've been seeing some of these changes unfold here on Earth, maybe as a result of that. There's some compelling evidence, at least in my mind, for that. So here we have a snapshot for, I think it's about the past 7 days. And this is really clearly illustrates the effects that the solar wind can have on the Earth energetically. So I just think this is absolutely fascinating. Here we see this high-speed stream come in. This is the solar wind, and everything that's behind the current moment is data that we collected, so observational data. We see our radiation belts were low charge right there, fairly low charge, maybe like moderate charge, because if you are in the greens and the blues, that's like a lower charge. So moderate flux before this high-speed stream came in, and then we see the solar wind velocity going up to 800 kilometers per second from that. It was very, very fast. We have another coronal hole high-speed stream maybe set to sweep by soon. We'll talk about that. But we see this go up really high. We see a little bit of perturbation in the belts there at the beginning. Here on the y-axis, we're looking at the L shell. And so this is the distance away from the Earth. Every L, like a 1L, would be 1 Earth radius out. So once you're at 3L, 5L, 9L, you're pretty far out there. And there's 2 radiation belts in particular. One is the inner proton belt, which is mostly proton dominant, so positively charged. That's closer to the planet. And then if you get further out, from about 3 to 9 L, like L3 to 9, that is the electron dominant belt. So we're mostly looking at electrons here. And so you'll see that we had this high-speed stream. Look at how the flux not only really increased dramatically, see the dark colors that we're reaching, especially right now, but also moved further out. So there's been this expansion of the radiation belts. Not only are they more charged, they're also bigger and more expanded. And so that could work with this coronal mass ejection impact that we have coming in and enhance the effects of that. This is not the strongest solar storm to launch towards Earth. It's only created from a 4.0 C-class flare, but it's still, we see this shock wave launching out. That's set to impact us early to middle of June 2nd universal time, so in less than 24 hours. And then we see our radiation belts are supercharged right now. So that is looking like it's going to be a bigger impact than expected. And if I show you our radiation belts right now with a different view, you can get a sense of how this energy has been charging up. Here we have our data from the Space Weather Portal from NOAA. You can see that they did kind of bottom out during that high-speed stream impact. Like we talked about, a little bit of volatility, but look how they've been charging up. And actually the last values there, it was greatest at noon. So when they're directly in front of the sun, or in front of the Earth by the sun, and that reached values of 1.74 times 10 to the 4, which is very, very high. This is the warning threshold. They're deadly. They're called deadly because these relativistic particles cause really strong ionizing radiation. So satellites in the radiation belts, especially if they get charged, they have to kind of manage that energy. You can have a phenomenon known as deep dielectric charging, which can cause problems in the circuitry. And if you get these particles to go in and create these charge potentials in the satellite, and then they arc, that could, of course, disable the satellite with a short circuit. So that's what this alert threshold is for. But if you were to, let's say, go in a spaceship and fly through the radiation belts, you probably don't want to do that unless there's some pretty heavy shielding, because you're going to get a huge dose of radiation. Just like you get more radiation when you're on an airplane because you're higher up and you're closer to all this relativistic flux from and you have less protection of the atmosphere from the sun. Well, if you're in the radiation belts, you're getting bombarded with these high energy particles. Each one can interact with molecules and create a cascade of ionization, thousands and thousands of ionization reactions where you're breaking apart molecules. So that's not good for you. You know, you're going to break apart a whole bunch of DNA, and there is some kind of debate out there. I'm not saying this is accurate. I'm just saying there is some debate out there as to how the Apollo missions worked in terms of us, you know, sending the astronauts through the radiation belts, and also that lined up with solar maximum. So it was like kind of odd that we did all these crazy moon missions when we had solar maximum and we didn't even know that these radiation belts really existed yet, and everything was seemingly all right. But I'm not saying the moon missions are not real, just that is one thing that people debate on is, well, the radiation belts, they're deadly. Like, if you don't have shielding, that's not going to be good for you. So how did that work? So that's just an example of why these are important. But they are one of the main factors involved with a geomagnetic storm, because if you get this push of energy coming in, it can cause them to precipitate down, charge up the Earth at a closer layer to the surface, and then that can drive a lot of changes like a geomagnetic storm and more. Let's actually look at our current geomagnetic field right here, just so you can see that it's actually all nice and quiet. And that's to be expected because we're not in the middle of a geomagnetic impact right now. But this could change within the next 24 hours. We'll just have to wait and see. But here we have our flux legend, and we see that all our values are actually fairly close to zero. You're always going to have a little bit more magnetic flux in the polar regions, but normally I'm showing this when it's like totally dark red, especially in these areas. But now, because we don't have that impact yet, you can see that things are looking pretty normal. But that could change, and I think it's likely to change in the next 24 hours. NOAA is forecasting a G1 storm from this impact within the next 24 hours or so. They think it's going to come in around early to the middle of June 2nd, Universal Time. And right now it is, or sorry, July. I keep saying June. Middle to early July 2nd, Universal Time. And right now it's July 1st. So welcome to July, everyone. Maybe you're still on June time like I am. But it is now the craziest month of the year, at least according to the astrological forecast. So buckle up, buttercups. But here we see this coronal mass ejection wave propagating out, pretty much aligned with the Earth. Some of it going here, but actually I think they may have updated this model. It looks a little bit more aligned than the first run that they did. And we also see it propagating here pretty much along the ecliptic plane. Yeah, they updated the model. It showed before more of a flank impact. So they've grown in confidence in terms of this coronal mass ejection hitting us. And we see this causing a pretty nice plasma density spike right there. A little bit of a velocity bump, but not much. It is fairly slow. We see the velocity is fairly similar to the high-speed stream right there. And they're showing us not even hitting the bulk of that velocity a little bit to the north. But that is what NOAA is showing. We can pause that exactly on the time of impact, which would be, let's do it right before it comes in. They're showing that actually at 1 a.m. Universal Time on the 2nd. So just like less than 12 hours away, according to NOAA. But if we go to the peak impact, according to their model, take it with a grain of salt, that's at 1300 Universal Time. So that's about 24 hours away. Here we can see the radiation belts, but this time we're looking from a 3-month perspective, all right? And you can see how they're at some of the very high values that we don't often see. So again, it's the same log scale right there. This is flux, so each one is an order of magnitude jump. You see that sometimes we're low and then sometimes we're high. And so back here in May, we were pretty charged up. There in April, we're fairly charged up. This is 3 months of data. And now you see that we're reaching some of these really high values again. Not the highest that we've ever reached, but still fairly charged up, especially after a high-speed stream impact. That's the sort of conditions that can create this sort of supercharging of Earth's radiation belts. And so sometimes you get a big impact come in and nothing happens. You see where our radiation belts were before we had that G4 storm in the beginning of June, right, from that impact, which could have been G5 if the magnetic field conditions of the solar wind were southward instead of northward. But you see how they immediately dropped and precipitated all their ions down to the Earth. Well, we're in a similar setup now, though the solar storm coming in is much weaker, but we see that we did get a strong storm, and this was definitely one of the contributing factors for that. So it's not something to ignore if you're into the space weather forecast. Impact for this should be around night tonight for North America. So if you're an aurora chaser or you want to get some photos, you may want to try tonight. It's very possible that we have activity. Go to the space weather portal from NOAA to stay up to date. That's linked in the video description. But go outside if you have low light pollution, that's best. And then point your camera north, put on long exposure. You may see something, but just point it north because you're going to have greater flux to the north. And I just want to show you a couple other things too. So let's see if this is the right video. Here's our 211 angstrom view. And this shows another coronal hole right there. So this is a dark region in the solar corona. The outermost part of the atmosphere has lower plasma density because the magnetic field is open. It's pushing out all these ions into space at a very high velocity. So it creates these high-speed streams just like the one that hit us. That one was transequatorial, so it was perfectly aligned. This one's pretty far to the south. I don't think it's going to interact with us that much because we've been seeing this coronal hole on the sun now for a few rotations, and its impacts on the Earth have been fairly minor thus far. But we do see that it kind of jogs up and has this transequatorial component there at the end of it. And we'll see if that strengthens over the next few days. That's about probably 10 days away from being geoeffective. This is closer because that has to go all the way from there to there. And it takes about 2 weeks to go from the limb to limb. So we're maybe like a week, probably at least a week, if not 10 days away from that passing us. A lot could change with this part of the coronal hole. It could develop more and get a lot bigger. It could also kind of close up and go away. So don't want to get too out there on a limb with forecasting this, but that part is getting close to that equator, and it's when you slice that equator and the high-speed stream is flowing exactly along the Sun-Earth ecliptic plane that you get the strongest effects from these sort of high-speed streams. Now, we can also look at our 304 angstrom view, and we see that things have been fairly quiet. We did have some big plasma prominences erupt off. We're going to look at that next. Interesting things there to talk about briefly. But in general, you don't see much activity on the sun in terms of like big launches of plasma. But notice that there's actually quite a lot of sunspots right now, all these bright regions. So sunspot numbers have come back. I can actually pull up the latest numbers right now, our daily estimate. I haven't looked it up, but we were at 150. We're probably over 150. No, we're right back to 150. So let me show you this. We have our finalized numbers for June. And this is what the sun was doing sunspot-wise in June. We see that we did drop all the way down to about 60 or so, charged up to 150, and then kind of bottomed out around 100, then are back at 150. So our estimated sunspot count for June is probably about 115 or so. And we might be able to see that already on the Space Weather portal. They update their monthly count, but sometimes they do it a day or two afterwards. So our May count was 79.2. This next one will be probably about 100, it's at least 110. I think it might be a little closer, like 112, 115. And as I talked about in a prior video, this solar cycle is very similar to solar cycle 13. So here we see this big spike actually to the same value as what we had in August. This one was also in August. This is 215. We had 216 for our spike. Then this drop just like we had in May, though this one is a little sooner. This one was in March. But then look at this rebound that occurred. So what could potentially cause that rebound? That is a good question. Let me pull up solar system scope for you to show you what could cause that rebound. But before we do that, I want to show you this very interesting plasma burst that occurred. And this was a big launch of plasma from the western limb where we have actually a lot of planets right now. But notice how it goes up like this. See the direction of that? What's so interesting about that is that that is along the field-aligned currents of the sun. So you have these localized magnetic field disturbances with these sunspots and then coronal holes that make kind of these open magnetic fields. But you also, just in general, have these field-aligned currents that kind of go up like this, especially during solar minimum. They're very well established. But you have these currents that just kind of flow out like this, and the model is that they flow out and then they actually connect down way further out in the solar system, maybe at like the edge of the heliosphere or even out in the Oort cloud. And then that electric current flows back in along the ecliptic plane. So this launch right there, not Earth direct in terms of it launching towards us right now, but the electric circuit of this is going to, we think, hypothetically based off of our models, that is going to travel up above the ecliptic plane of the solar system. Eventually that electric field gradient will take that plasma down to the ecliptic plane where it then flows inwards. And so it's very possible that some of that energy in plasma will flow by the Earth backwards, basically, passing through all the outer planets before hitting us, and also all the TNOs and anything else that's in that zone, passing through that before it sweeps by the Earth and then Venus and then Mercury before reaching the sun again. And that is kind of an unknown time as to when that could occur. I don't know the transit of this whole process. It could be 2 months from now, then that could sometimes you get these unexplained minor solar storm shocks that kind of come out of nowhere. This very well could be the mechanism explaining that. So I want to do more research into that to really get that idea nailed down to see whether that's accurate or not. But at least that's a model of energy flow for the electric and magnetic field circuit of the solar system of the sun, according to Hans Alvin. I'm reading that in his book, Cosmic Plasma, which is a fantastic read. But let us look at Solar System Scope, which is our application we use to examine planetary geometry, because I've also been doing some research on planetary resonances and how they affect the sun, solar activity. It's really fascinating stuff. We'll go into it just a little bit right now. But you'll notice this perfect alignment with all the planets: Neptune, Saturn, Ceres, Venus, Mercury, Mars, and then we have Earth and Jupiter there about opposite each other. And this is all forming effectively a square. Now, what's so interesting about this is that the planets have gravity and the sun has gravity. And a lot of people discount the effect of gravity, especially in the space weather community. A lot of people only talk about magnetic fields. And then you have the electric universe people, which only talk about electric fields. And then no one's talking about gravity and its effect. Well, gravity is not as strong of a force as the electromagnetic force, undoubtedly. Doesn't mean it's insignificant though. It drives some of these base processes. So it's more foundational in some aspects. And so the sun here actually orbits around the solar system barycenter. Everything in the solar system orbits around a fictional point actually. So the sun is being moved around the solar system barycenter because the other planets have mass. And so they tug and they create this actual point of central rotation in the solar system. And what's incredible about the solar system, the planets, is that it is a perfectly orderly system. And so all the different planets, they're sometimes rising above the ecliptic plane of the solar system in general. They're all along this plane that we're looking at here, right? Let me even slice that for you. See that? We notice that most everything in the solar system is traveling along the ecliptic plane. So if you look at Pluto, it has this different orbit. And some of the TNOs, see Pluto's orbit going up here like this. You know, it really has a higher inclination. But with all the planets that we've looked at, even with like dwarf planet Ceres in the mix, even though they're all exerting different forces and pushing and pulling on the sun different amounts and each other, the net angular velocity and the overall force balance is like perfectly zero at all times. So there's an equal and opposite kind of force at play for any single given planet. Jupiter is the most significant planet as it relates to this. So we're looking at the gravity of the sun being a huge influence over the barycenter because it's located very close to the sun. Sometimes it's like 2 solar radii away, but generally the solar system barycenter is like right in this sun zone. So it's, of course, the main dominant influence. It's 99.86% of the mass of the solar system. But Jupiter is number 2. Jupiter is really important as it relates to the solar system barycenter. And in fact, it's Saturn and Jupiter that are the main controllers of that. But what they found with this planetary resonances research is that everything within 5 astronomical units effectively has its own grand symphony. So you have all these resonances that occur with the Earth and Jupiter, Venus and Jupiter, Mars and Earth, and Mars and Venus, and Ceres and Earth and Venus, and all of them have these different specific resonances, these gravitational tides that they create. And if you look at the entire 5 astronomical unit zone, they kind of form a grand symphony that seems to line up with solar activity because of these gravitational tides that they create. And these tides, like spring tides on Earth, right now we're in a quarter moon, by the way, so happy quarter moon. These tides affect the plasma on the surface of the sun and also deeper in. And so when you get really strong tides, that is going to cause there to be perturbations to the sun and therefore kind of like solar activity. So these rhythms really line up nicely. Now what's interesting about this as well is that Jupiter is the biggest heavyweight in terms of plasma, but here we're talking about gravity. It is the conductor of this inner symphony. And these resonances are really linked to like the 12-year cycle. Venus is actually really interesting too because she's about the mass of the Earth, but she's closer into the planet, to the sun. And so she has a stronger tidal effect on the sun than Earth does. And then Mercury is especially interesting because while it's not massive like Venus or Jupiter is, it is the closest planet to the sun. So it is the final tug on the barycenter that controls the overall position. And so that's like it's like the final kind of piccolo playing in the the symphony, adding that high note on everything. That's Mercury. So Jupiter, though, you'll notice, is conducting the grand symphony with the inner planets, but it's also the planet that's the most massive and closer to the outer planets. And there are resonances created between Neptune and Uranus that line up with the Gleisberg cycle, which is about an 88 to 100 year long variation in solar activity that modulates the shorter solar cycles, like the 12-year one. So if you have a Gleisberg low, then you can expect the solar cycle to be weaker than it would be otherwise. That was like the last solar cycle 24, maximum going from about 12 to 14, somewhere in that range, right? The early teens of the new millennia. Well, Jupiter is furthest out from this group there, so it's also able to coordinate with Saturn, Uranus, and Neptune. So it really has a position of being a grand conductor in this solar system. If it was further out, it wouldn't be able to conduct as efficiently with the inner planets. So it's in the perfect position to basically be a dancing partner with the sun and coordinate all the extras and the backup dancers and everything like that. But you notice here this alignment, and the only thing on the other side of this, like all these planets there, all over there, the only thing on the other side is Earth and technically Pluto as well. So this is very interesting. And as a result of these tidal forces and this alignment, I think we can expect some sort of change in solar activity to get triggered. And if we go back to our solar cycle, well, we see that we have this peak there for solar cycle 13 after this drop, and this solar cycle is almost exactly identical to ours thus far, solar cycle 25. And we see these repeating rhythms across time as well with planetary resonances. So 1894, let's go to that month. Let's see what the planetary resonances look like for that month. That'll be an interesting little experiment really quick. Let's just pull up. Okay, so we want March of 1894, around that time frame. And this can go back there, just take some time. So let's just scroll through. I like doing it live. We're doing it live, folks. Hello, welcome to the live stream. If you're new here, I'm your host, Stefan Burns, geophysicist, space weatherman, and more. And we look at look at that. We look at all the things in our reality that could be affecting us energetically as best as possible. This is July though, so we can use Earth here to scroll back to April, I believe it was our drop. Yes, let's go back to April. Oh, look at that. Oh, wow. Wow, you couldn't have, you can't make this stuff up. I've never looked at this. This is brand new. But look at that alignment we have in April. We have Neptune, Pluto, Jupiter, and then the Sun, Mercury, Venus, Mars right there. Slightly different the fact that we also have Saturn and Uranus kind of aligned with the Earth. But in general, very similar setup, at least in terms of like the alignment of planets on one side. It's kind of like this, a little bit of like a bisecting line, a little angled as well. But that's very similar. And then if we zoom forward to the next few months, then we see actually some nice alignments right there. This is back in 1894, Jupiter, Neptune, Earth alignment. And we have right now happening a Saturn-Neptune alignment. So yeah, similar planetary resonances. Keep your eye on that. I'll be releasing a lot more video on these planetary resonances. I really think it's kind of the key, one of the big keys to solar activity. You could also zoom at that perspective of, okay, well, you have the planets and the sun all interacting together gravitationally, and they're all perfectly, effectively balanced. But what happens if you get like a rogue red dwarf to sweep by our solar system? And maybe it's not even an ultra-wide binary companion. It's just a one-time swing through the solar system. I mean, not through the solar system, but nearby. Let's say it gets within like a light year, or even like gets to the edge of the Oort cloud. Imagine how that would affect the gravitational balance of the solar system, because we're just a single star here, right? A lot of stars are like binary, triple, even more. That's really complex stuff. It's going to be difficult probably to manage all these planets and also have life. But a single star, nice, calm overall, balanced system. Jupiter there doing a lot of work for everyone's benefit, you could say, in the solar system. But you get this, let's say, rogue red dwarf to sweep by. We've had it before. I think there was one that occurred about 70,000 years ago. We have another one coming up soon. By soon, I mean like I think 10,000 years or something like that. Could be 5,000 years from now. I talk about that in my Planetary Resonances e-course. You can sign up for that by clicking the link in the video description. Really good foundational stuff if you want to understand this. If you just quickly look at our earthquakes, nothing as like super crazy has popped off in the past 24 hours, but I just quickly want to highlight, and let's just switch this to map view. I just quickly want to highlight that we have 2 ongoing earthquake swarms. One there south of Japan has been going on for more than a week now. Some of these earthquakes are big, 5.4 right there. And then we also have one over here. So this is fairly close actually to that location of the 2004 magnitude 9 earthquake. It's not exactly there, but it's to the north, but a lot of earthquakes with this earthquake swarm there. So this is active. And what's special about earthquake swarms, like these magnitudes are just in the 5 range, which is pretty big, but it's not like a magnitude 7. You'll get a lot more energy release from a higher magnitude earthquake than you will from this entire swarm. But what's special about swarms is that it's a continuous kind of rumbling that's shooting that energy out. So we have this swarm there in just there off to the east of India, and then we have, and also I think this is, yeah, in Indonesia, to the west of Indonesia, near Singapore, and then we have the swarm there just south of Japan, and we have effectively these 2, this is a little difficult, we have these 2 seismic energy wavefronts kind of converging in this Taiwan and Hong Kong area, and then we also have been having some big earthquakes in the Philippines, also basically triangulate these positions. Like maybe this is a zone that we have to kind of watch for a more significant earthquake over the next week or so. It depends on how long this all continues. But that's just kind of an interesting thing to point out. These earthquake swarms both occur at the same time, fairly close together. One thing to point out too, if you're wondering, if you're looking at the proton flux, these bumps here are from the fact that the electron belt, the radiation belts are so supercharged. So you get this sort of proton enhancement. It just kind of oversaturates the sensors. So these aren't actual bumps in proton flux. It's kind of like a sensor error, but that's just because the radiation belts are so charged up right now. And I believe that is it. I think I have, do I have another video for you? No, oh yeah, no, that's it. So thank you all so much for watching, everybody. Hope you're all doing well. I am traveling to go see a friend, Eileen McCusick, who's been on the channel. We're going to do a whole bunch of stuff with the biofield, create some content, talk to Robert Temple, the author of A New Science of Heaven. So I'll be driving for the rest of the day, and then I am going to be busy basically till Sunday. I may be able to release a video or not. So again, this solar storm impact is likely to happen, but it's not guaranteed. But that's probably within the next 24 hours. So I hope that goes well for you. If you're someone out there chasing aurora, then I hope you get some good photos. And I hope it actually occurs in the first place in terms of the aurora getting to your latitude. And I've been your host, Stefan Burns, geophysicist, space weatherman, and more. Wishing all of you well. Please take care of yourselves. I'll see you all in the next video.